Hello everybody. In this video, we are going to solve a problem on Leetcode Live. We will pick a problem of easy difficulty level today. I have already filtered the list by easy difficulty level. So let's pick the first one, which is 2-sum. Okay, let's read the problem and make sure we understand it. Given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target. Okay, you may assume that each input would have exactly one solution and you may not use the same element twice. You can return the answer in any order. Okay, so yeah, I think it makes sense. Basically, they are given an array of numbers and they have given a target, and we have to find out the two numbers which add up to that target, and we have to return their indices. Yeah, that is the thing to be noted, is that we don't have to return the numbers themselves, 2 and 7. We actually return their indices in the input array, so 0 and 1. And they are guaranteeing that there is exactly one solution. So there will be exactly one pair that adds up to the target is guaranteed to us. Okay, so we already went through that example. Let's look at the second one. Nums is 3 to 4 and target is 6, and 2 and 4 sum up to 6. So we return their indices, which are 1 and 2. Makes sense. And then nums is 3 comma 3, target is 6. Yeah, 3 plus 3 is 6. So we return 0 comma 1. Okay, let's look at the constraints. So the constraints are that the length of the nums array is between 2 and 10,000 inclusive. Okay, the values in the nums array are between -1 billion and +1 billion, yeah, inclusive, and that is well within the range of a 32-bit signed integer. I believe the range of 32-bit signed integer is roughly about -2.1 something billion to +2.1 something billion. Anyway, and then the target is also between -1 billion and +1 billion, and there is only one valid answer. They already said that, so they are also giving it as a constraint. Okay, follow up. Can you come up with an algorithm that is less than O of n squared time complexity? So yeah, it looks like I mean, maybe most of you figured this out. Is the most simple way of doing this is probably just like take every number in the input array and find its complement to make the target sum in the remaining array by just linearly scanning, right? And it will be two nested for loops, and it will basically be of n square complexity. But let's not go too fast. Let's try to actually implement that approach. And before we implement it, just very quickly, for the sake of completeness, let's lay out what we are trying to implement, right? So what we are trying to implement is, if we are given an array like this, we take 2 and we say, okay, hey, what is the remaining sum? And the remaining is 7. And we just search for 7 and 7, 11 and 15, the remaining array to the right side of 2, right? In this case, 7 appears first, but if the target was like 17, then we would have to search all the way to the end, right? And if we had not found it, then we would take the next number 7. We would take remaining in this. Let's say target is actually something else, right? Let's say target is equal to 26 actually, right? So here remaining would be 24. We wouldn't find it. We'll go to 7, and then remaining would be 19, and then we would search 11 comma 15 for that. We wouldn't find it. Finally, for 11, remaining would be 15, and then we'll just search array of size 115 and we'll find it, right? So that is our algorithm, pretty straightforward. Let's try to implement it. And whenever I implement like multiple approaches, it's always good to implement them like, simple scan, right? Something like that. We implement it in a helper so that we don't have to remove it. It can actually stay there just for, review purposes if need be. Okay, so here let's begin. So we have to consider each number in the array, right? Each number in the nums array. So let's write one for loop. It says I equal to 0, I less than nums dot length plus plus I. Okay, and then we say num equal to nums of I just like doing that. Like you could directly use nums of I wherever we use num, but either ways. And then we say remaining equal to target minus num, right? So that's our remaining, and then we run another loop, but this time we start from I plus 1, right? I plus 1, we only have to look to the right, and that's because if it is not obvious, if there was a number before us with which our addition makes the target, then that number would have found us, right? So we don't have to really look for the whole array. J is less than nums dot length plus plus j. And here we say if nums of j equal remaining, then we just I think we can just do this, return new int. I hope I remember the array initialization syntax. I think I comma j are the two indices, right? We are returning the indices. Every language is slightly quirky array initialization syntax, but I believe this is the right one in Java. Okay, and that's pretty much it. Now, they have said that there is exactly one pair which will add up to that number. So this statement will be executed for at least for exactly one thing, right? But in Java, like we can't just leave this blank outside the loop. Java doesn't know the semantics of the inputs in the problem. So here we have to either return or throw something. Otherwise, Java compiler is going to complain that all code paths do not return a value. So we are just going to throw some exception, and I think it's either illegal argument exception or I always switch between C# and Java and I forget, but I think this is the right one in Java. No pairs sum to target, which is an illegal input for us, so we are going to throw it. We don't have a default answer like what 2D array should we return. Like the problem statement doesn't say we should return -1, for example, so we should be throwing here. Okay, now let's try to call that here. Simple. Oh, I'm missing an L here in simple. Okay, simple scan. Excuse me. And target, right? Yeah, I think that should work. Let's actually try to run the code and see if it works. I mean, when we write so much code without an IDE, there could always be like compiler errors. Return to some. Oh, there you go. That's the thing. Too used to autocomplete. Okay, there you go. So we did pass all the test cases here, and we should add our other test cases, like we said, like 7,7 or something like that, where duplicates are there. Like for example, actually in this case, 7,7, it should allow 14, and otherwise it wouldn't, right? So they have given that we shouldn't reuse the same element, but you are allowed to use that 7. So yeah, there you go, 1,2. Yeah, okay, looks good. Now let's talk about the follow-up they have asked, right? I'm sure if you try to submit the solution and let Leetcode look at our performance compared to all the submitted successful submissions, our time will be not very good, right? And that's because we haven't implemented a better approach. Well, whenever there are problems like this where we are given an array and we have to find something and we have to find a lot of things, of course, sorting is always comes to mind, right? Like if we spend the time to sort once, then every other find becomes log n. So of course, that can be an approach we can take. We can. There is one tricky bit here, but laying out that approach before I talk about the tricky bit. So, if you are given an input, let's take a different input and a longer one, slightly longer one. Let's say we have 17, 3, 15, 9, and 22 and 100, right? And let's say the target sum is, or let's not worry about the specific target sum, but if we were looking for two numbers which added up to a specific number, like without doing or in a better complexity than O of n square, then sorting would be nice because we are repeatedly trying to find things, right? For a given number, we are trying to find its complement number. So let's sort this, and by sorting this, we'll get 3, 9, 15, 17, and 22 and 100, right? And now it's easy, right? We spent O of n log n time in sorting already, so O of n log n time. But once we do that, then what happens is for 3, in order to find its complement number, for example 22, if the target sum was 25, in the remaining array we could do a binary search, right? And that would be log n. So we are doing n operations, one for each element, and each of those operations is doing a log n operation, right? Log n operation. And so our that step is also O of n log n. So our overall time complexity is a overall n log n, right? We did one n log n for sorting, and then we did another n log n to actually find the exact pair that we are looking for, and that would work. And now, but here one interesting tidbit in implementing this approach is that they are not asking us to return the two numbers, they are asking us to return the indices. So it's kind of a little bit more complicated. The approach will be still O of n log n, but the implementation is a little bit more complicated, and we have to be much more careful. And the core approach is still the same. So let me explain what I'm saying, right? So let's write this down again. So let's write down these indices 0, 1, 2, 3, 4. I don't like double digits because it's making my formatting off, but okay. 0, 1, 2. Let's just do this. 0, 1, 2, 3, 4, and 5, right? So these are the indices of all our numbers, right? Now we have to return the indices. So we actually not only we have to sort the numbers, we also have to sort the indices along with them, right? So we actually keep the indices with them. Okay, what is index of 3? The number 3, it's index 1, right? What is the index of 9? It's 3. What is the index of 15? It's 2. And what is the index of 17? It's 0. Sorry, and then 4 and 5 stay the same, right? And that would be what is needed. And the reason is because ultimately when we binary search, we still binary search in this nums array, but when we find its complement, instead of returning their indices from this sorted array, we have to return their indices from this indices array, because those are the original indices that the user is looking for, right? So anyway, I'm not going to try to implement all of that. It's going to, it probably maybe in a future video there we can easily do this by, implementing a custom comparator in Java. There are things like we have to convert ints to integer objects, because whenever we use a custom comparator, those can only be used with arrays or collections of objects, and not arrays or collections of int or some basic data types like that. Anyway, so that's that approach that would work. Now, there is always another approach, right? So there is, let's say, approach with sorting and binary search, right? And the other approach, obviously, again, when we are looking for when we want to fast look up whether a specific number exists in a collection, we can always use hash maps, right? We can insert all the elements in a hash map, all of these input ones, right? And then we can say, okay, hey, 17, what is the complement of 17? Let me see if that exists in the hash map, and that will be often inserting all of them in hash map is going to be. So let me actually exemplify that here. Approach, actually, let me just start a new comment. Using hash maps to make lookups O of 1, right? And so we put all elements in the hash map. Actually, we should put it incrementally, but I'll come back to that in a minute. in the hash map, which is O of n, right? And then for each element, we look up their complement in the hash map, right? And that is going to be O of 1. And so this is O of n is for each element, and O of 1 work inside that O of n loop, right? So O of n, and then inside that we do O of 1. And so that becomes an overall O of n complexity, the whole algorithm. Now, of course, in this case, we traded off memory for a better time complexity, which is O of n versus O of n square. And that could be a good trade-off, right? Uh, Actually, one very interesting thing to consider is that when a user gives us their array, right? For, let's say here, this is the public function. The user is giving us their array and their inputs and asking us to do something that presumably only needs to read the values in the array, right? We cannot destroy the array of the user or rearrange. I mean, by destroy, I mean we cannot just sort that in place for the O of n log n algorithm, right? It's not a good design. Now, in special circumstances, maybe we can if the calling code and this code know each other very well, and they know that this is going to actually change the elements in the array, sure. But in most cases, that is not a good design. So anyway, if we are going to sort or do something with the elements in that input array, we should do it in a different array, which means we are going to use extra memory, O of n extra memory. So it's not so terrible that we are using a hash map in this case, which will actually use some extra memory, right? Okay, so let's try to implement that approach very quickly. It should be pretty fast. Actually, there is one more thing I just wanted to cover, which is with hashing. I'll come back to that in just like a second after I write this. Let me declare the hash map first, and then I'll come back to that. So the key is an integer and the value is also an integer, because the value in the hash map is going to be the index of that element in the original array, because that's what we need to return, right? Map equal to new hash map. And yeah, in Java you can do this. It will implicitly figure out the data types of the generic arguments. Okay, so here what I was trying to say is that instead of trying to dump all the elements in the hash map and then looking up, we need to do it slightly differently. And that's because, let's consider this example for a minute, and I'll change the element values of there just to exemplify my point. So let's say there is a duplicate in here, 9, 9, right? And then the target sum is 18. Well, actually there are two combinations that make it 18, but let's say this was like 16. Okay, so 9, 9. Now, how do we handle that? If there are two nines or more nines, then we are allowed to use other nines to make the sum. But if there is only one 9, we don't want to be, using that or twice, right, to make a sum of 18. And if we dump all the elements in the hash map first, and then we are actually going element by element and looking its complement, then 9 will find itself. Now, there is a way we can do it. We can remove that element from the map, then kind of, look for the other one and then add it again. But the easier thing to do is actually just incrementally add and look up. Okay, so here is what I'm thinking about. Okay, so for int I equal to 0, I is less than nums dot length plus plus I. And what we do here is we say, okay, we first look up or calculate the remaining of that number, and that is target minus nums of I. And then we say, we first check whether the hash map already contains that. We can do contains key, but if actually we want a method which, if it is there, it returns us the value as well. And I think there is a method like that in the hash map class in Java. One second, let me look it up. So let's say integer remaining index, right? Because if the hash map has that, it will return us the value of the key. The key is the number, the value is the index, right? So map dot, what is the method? One second. Java hash map. Okay. Hash map. Contains key is fine. We could use that, but then if it is there, then we again have to call get or something. Oh, get or default. That's the one I'm talking about. Okay. So what I mean here is a get or default, and then we give it the key. What are we looking for? We are looking for the remaining number in the hash map. Is it already there? And if in the default we want is null, and remember it's a hash map of integer objects, so null is a valid value for this, right? Okay, so in one go, what we are saying is, hey, map, go and look up the remaining number, and then if it is there, give me the value of that key, otherwise give me back null, right? So if rem index is not equal to null, then we are just returning new int of the array is, well, our one index is I, and the other is rem index dot the integer inside it, I think int value, right? Yeah. Okay. And otherwise, if not, we add ourselves to the hash map, right? So we say map dot put, and what is the key? The key is the value. So key is nums of I, and the value is the index, right? Because that is the number is the one we want to look up really fast. I think that is actually all. Like above, Java wouldn't like it if we didn't do a return or an exception here. So we do that. We say no pairs sum to target. Okay, there you go. So let me just kind of run through this and see if it works. Oh, cool. So it, oh wait, I haven't called that yet. Obviously it worked. Okay, do some with hashing, right? That's the one we want to go. Okay, cool. It was accepted. Yeah, pretty straightforward approach, so not hard to code. Let's submit this one. I'm not afraid to. I was afraid to submit the previous one, but I'm not afraid to submit this. Okay, there you go. So we are beating about 98% in time, and we are also beating 65% in memory, although memory one I don't trust very much. The Leetcode's analysis, or at least it doesn't mean much. I think a lot of the submissions will have similar memory usage. Okay, hopefully that was helpful. In a future video, like I said, I could, if there is interest, I could actually end up implementing the binary search approach with those indices sorting and everything. Let me know in the comments if you want me to do that. If you're liking what I'm doing in this channel, please consider subscribing to my channel, and please thumbs up this video. I'll really appreciate it. See you guys next time.